So, welcome back student. Last lecture we have basically talked about few mechanism based strategies and we said that there are very unique transformation or unique transformations are known in the literature where the mechanism is very key. If you know the mechanism of those transformations, you will be able to formulate what kind of functional group interconversion you will be able to do with those transformation. So, we will try to simplify those strategies with some case studies. Now, initially the problem which I will be now analyzing, it is a very straightforward problem. We say a target molecule was given to you whose structure is this structure. It is a bridged bicyclic compound, a cyclohexane is the core structure, you have a two ring bridge CH2 CH2 and this end you are having a CO2 Me. So, basically a two bicyclic are fused, you have a quaternary carbon where a ethyl group is there. The starting material I say okay, I am giving you the starting material which is this kind of starting material and this starting material. Now, the way I have drawn the starting material, it basically gives you that probably if you can simply do a double Michael addition, Now, this double Michael addition, why I am saying it, if you see the structure, the left hand side compound is a Michael acceptor, the right hand side is a Michael acceptor, but in addition the left hand side compound can have a acidic hydrogen here. So, these hydrogens are acidic. So, which can be easily picked up to generate a nucleophile. So, if you pick this hydrogen to generate a nucleophile, it let attacks here. Now, once you attack here, this negative charge now comes here. Okay. Now, this negative charge now acting as a nucleophile and attacks in a Michael fashion to this carbon. So, basically if double Michael takes place, your synthesis is quite attractive and is quite feasible. Now, this compound is commercially available, even you can make this compound starting from this 1,3-cyclohexadione, probably this chemistry we talked about many times in our class by allylic disposition, allylic transposition. This compound methyl acrylate is commercially available. Now, the point is the molecule is definitely not a complex molecule, it is a medium sized molecule, it is a bridged molecule, but if you do the retro in this way, that what I am doing, we do the retro, let us say we first cut these things this way. So, we write double bond O this and this part we write in this way, the core cyclohexane we write it this way. We say we will disconnect here as well as here. So, now we will put now this Michael acceptor. So, here you are having a delta minus which can be easily generated and this part if you put a double bond, this is basically a electrophilic carbon now. So, initially once first Michael starts, then this minus will come here. The anion is basically transferred or relate from this carbon to this carbon. Now, this carbon is now gets this Michael acceptor in its close proximity and it undergoes another round of Michael to complete the synthesis. There is also another way through which you can visualize the entire synthesis. I will try to analyze whether this molecule can be disconnected in another way. The answer is yes, definitely you can do it. Now, see how we can do it. Next I am saying probably if you have this kind of structure or this kind of diene as a Diels-Alder 4 pi system, you can easily do a 4+2 cycloaddition by simply doing this that is absolutely doable. And now, this compound can easily be constructed if you have this ethyl. So, what you do? You basically first picks up this acidic hydrogen by a base LDA, you initially get the enol or OLI. This one now you react with TMS chloride, trimethylsilyl chloride, you get the enol silyl ether OTMS, and this is basically you are acting as a diene. So, now you react with the ethyl acrylate in 4+2 fashion. So, eventually what you will get? The bridge structure will write in this fashion, you get this CO2 ET, you get this ethyl, you get a double bond with this OSI Me3. Now, we say if you react with a fluoride source, you basically give the oxygen silicon cleavage and then it comes back, it basically protonates to give you the enol, which is then tautomerizes to give you the target molecule, which was this structure. This will be CO2 Me. So, it will be CO2 Me. We put CO2 ET. So, similar basically CO2 Me. So, now I say that by this mechanism it is evident that a double Michael is equivalent to a 4+2 cycloaddition, is not it? So, in terms of FGI, a double Michael is nothing, a 4+2 cycloaddition. So, we have shown this by a example which gives you a very nice demonstration how a bridged compound can be constructed from a same starting material. The starting material in both the cases are similar. We use this 3-ethyl cyclohexenone for both the cases and methyl acrylate as a dienophile. So, we will keep on continuing our discussion with similar kind of mechanism based strategies. Now, what we are trying to do, I will give you a target molecule whose structure is a 5-member based aldehyde target. The starting material I am keeping at the extreme right hand side. The starting material also given to you. The starting material is basically named as alpha pinene. There are 2 methyls here in between. Its named is alpha pinene. You have a 6-member ring, you have a bridge structure, you have 2 methyls here. In between there is a 1 methyl, there is a 1 methyl. So, now if you count the number of carbon, everything remains same. You are having a 6-member with 4-member bridged. In this compound only the 5-member thing. So, means that some kind of fragmentation was taking place. You have 5-member here, you have a 6-member and 4-member. So, basically a new ring, new size of ring might be forming by some different kind of reaction. Now, what I do? We write this particular cyclopentane based compound in a different way. We say let us write this compound CH2, is a 1 carbon less, is basically CH2CHO, CH2CHO, and then this compound is basically nothing, this methyl, you have a double bond. So, this compound was basically rearranged to write in this way, because that will basically formulate how you can go back literally. Now, I am saying that this compound can be constructed if you having a something like this. Now, what is this? This basically a 2 methyls are here, methyl. Now, what I am saying? Now, if this particular bond undergoing fragmentation, it undergoes fragmentation. This Lewis acid comes here, it basically fragments to give you a this fragmentation, and then it gives a negative charge here, and this negative charge basically now quenches this positive charge to yield this product. So, this is a purely mechanism based things. Now, what is La? La basically stands for a Lewis acid which you have used earlier. Now, if this kind of rearrangement reminds you something that okay, let's continue our another round of retro. Next retro is, which I said, okay, this oxygen is coordinating with the Lewis acid, fine, and then now what I am doing, I am putting a or rearranging another carbonium ion in this way, putting this methyl here, and now I am saying that this carbonium ion is having this structure. Now, the point is, if you have this carbonium ion intermediate, as it is a 6 member and 4 member, probably it try to rearrange through this 1-2 fashion. So, this bond migrates to give you a 5 member system. Now, this carbonium ion now is definitely is not that much stable. So, what happened, this Lewis acid now trying to fragment it, the bridged bond, it will give you fragmentation here, and when this bond fragments, the electronic part of this particular bond remains here, and that will basically quench the electron deficient carbonium ion to give you the olefin. It is a purely mechanism based strategy. Now, we will try to find it out how the structure was linked. Now, I am saying that okay, this is almost close to the starting material. How you can formulate? You have 2 methyl group which I am writing in a green color, and if you have a epoxide something like this. Now, epoxide opening to Lewis acid through Lewis acid. This is a very classical reaction we call semi-pinacol pinacol type of rearrangement or manual type of rearrangement. So, basically in principle is nothing, it is a basically semi-pinacol pinacolone rearrangement or a manual type of rearrangement. Now, this epoxide you can easily construct it from this alpha pinene through a MCPBA based FGA. So, now we write the starting material, this 2 methyls are here. So, do the epoxidation with MCPBA by standard FGA or FGI, and then here you use a Lewis acid. Normal Lewis acid which was preferred is boron trifluoride diethyl ether, and initial coordination basically opens up the epoxide to a more stable 3° carbonium ion. Then this 3° carbonium ion basically will undergo 1-2 migration to give you the more stable ring structure. The 4 member ring seems to be pretty much unstable. Then this ring structure will migrate in this way to give you a carbonium ion like this. Now, this carbonium ion will definitely now tries to undergo fragmentation. This fragmentation is important, which probably is not a common part of this semi-pinacol or pinacolone rearrangement or manual rearrangement. In manual rearrangement, we never had this fragmentation. We basically have the migration or rearrangement, but this is a migration or 1-2 migration followed by fragmentation. So, that was very unique reaction, makes this reaction as a bit unique one. So, in this way basically you can simply formulate how this mechanism driven pathways is operative for a particular set of reaction. Next problem is basically not a mechanism based strategies, but you can fit it. Eventually, it is just a pure demonstration of functional group based transformation and other transformation. I put a 5 member ring and 7 member ring and this kind of way. So, I say that this is your target. The starting material which I am giving here at the extreme right hand side. I am saying the starting material which is given to you is basically having this starting material which is basically a tetrahydronaphthalene derivative. Now, see the structure, it is basically O-methoxy, OMe, initial starting material. Now, we will initially let us do the retro. Probably at the very beginning, it is a we will initially talk about a simple Aldol transformation. Now, how? We say if you have a dicarbonyl compound something like this, now this dicarbonyl compound is pretty interesting. It is basically a 1,3 dicarbonyl compound. So, you might expect that this hydrogen is much more kinetically acidic. So, immediately it will be picked up and then this will attack to this carbon, and now this is basically 1, 2, 3, 4, 5 and the right hand side ring will be 1, 2, 3, 4, 5, 6, 7. So, this aldol dehydration basically we are talking about. Okay. Now, this diketone, if you now do the next retro or next FGI, we say the FGI for diketone is very interesting. You can basically do a oxidative cleavage or ozonolysis, oxidative cleavage or ozonolysis. Now, how do we are going to do it? We will try to correlate with the starting material which was given to you. We say something like this, if you are having as an intermediate which will immediately give it to this intermediate, it is fine, this part is fine. Now, try to correlate with this starting material, the starting material was given here. Now, this is basically reminds you that if you have this kind of compound which basically undergoing enol ether hydrolysis and can give you this kind of ketone. Now, this ketone has a tremendous tendency to isomerize here, because this is a the rearranged one is alpha beta unsaturated ketone, but eventually you no need to take longer time, immediately you subject to the ozonolysis. Fine, here now you will be doing a Barchi reduction of the parent compound. Now, Barchi reduction, the mechanism all of you are familiar, and we have also explained earlier that if you have a electron releasing group, the regiochemistry was explained to you. So, the regiochemistry basically for electron releasing group you get this regiochemistry, this compound. So, Barchi reduction is a very useful reduction. So, now this entire transformation you can basically formulate what things you need to know. You need to know a Barchi reduction, the transformation, but the point is the mechanism you have to emphasize, that if you having a electron releasing group in one of the aromatic ring, what particular regioisomers you are going to get. This part is very important. So, once this part is done, remaining thing is absolutely simple. You just do a FGI through enol ether hydrolysis, oxidative cleavage and complete the synthesis. So, it was very obvious, and those kind of synthesis can easily be done. We will try to conclude the whole session just by giving you another example. This example is little bit different than the others, because the compound here is a benzene ring fused with a cyclobutane thing as a target molecule. Now, here as I said, this kind of transformation you can easily do with the help of multiple transformations or several key transformation coupled together. There might be many other pathways, but here Bn stands for basically benzyl, Bn stands for benzyl. So, initially what target, I am not giving you the starting material initially, I will okay, otherwise I will let me give you the starting material also. I am drawing the starting material here. The starting material is something like OBN, Br and CHO, OBN, Br and CHO. So, this starting material I am giving to you. Now, I am saying that the retro which will be now devised here, I put something like this retro. I say the cyclobutanol can be synthesized through a intramolecular organolithium coupling with this lithium with this aldehyde. So, it is a FGI, fine. Now, this aldehyde, now see how I am doing it. Which is this lithium will be can be generated at a later stage with the exchange of butyl lithium or tert-butyl lithium to give you the lithium, this organolithium species. Now, here I say if you have this epoxide you can basically do a manual type of rearrangement or the rearrangement which you have just discussed, that BF3 or Lewis acid mediated semi-pinacol pinacolone type of rearrangement will give you this compound. The mechanism probably now you are quite familiar. Initially you have to coordinate with the Lewis acid and then now open up this particular epoxide. So, initial suggest that you can basically opening up this thing by putting a hydrogen or putting a carbonium ion here. Then one of these hydrogen here migrates and you get this aldehyde through a manual rearrangement. Now, find here now how you can access this particular aldehyde or this particular epoxide. Now, you say that if you have this compound COCH3, you can easily do it. Now, the particular reaction we already explained long ago is called Cora-Tchaikovsky reaction. So, Cora-Tchaikovsky reaction of this ketone will give you this epoxide. Now, these things is now quite similar to the starting material. What basically you need to do now, you just do a methyl magnesium bromide and oxidation, it is FGI. So, in formal pathway we now do the formal or the forward pathway. So, we start from this compound OBN Br CHO, methyl magnesium iodide, I say PCC oxidation will basically end up with this ketone. Cora-Tchaikovsky reaction. So, basically trimethyl sulfonium iodide and sodium hydride will basically get the corresponding epoxide, you get this. Now, you put the BF3 thread for your manual rearrangement. So, initial you open up the epoxide O BF3 minus, you have these things, there are two hydrogens, one hydrogen migrates here. If one hydrogen migrates, you basically get a positive thing here and this positive things now quench this carbonium ion, you basically get the OBN, Br, methyl CHO. So, mechanism of manual rearrangement is very crucial. So, if you are not sure with the mechanism of manual rearrangement, now you exchange this bromide with this lithium with a sterically bulky lithium group like tertiary butyl lithium, and then you will find that you will generate a lithium species in the phenyl ring, and then your CHO is here. It will immediately undergo intramolecular nucleophilic reaction with the aldehyde, and then basically you get this cyclobutane derivative, benzocyclobutane derivative. So, by this way your target molecule can be easily achieved. Now, if you are trying to give you the key message or key information, the key message is your mechanism of manual rearrangement is very important. Mechanism of manual reaction, that basically gives the main foundation that how you can carry out the entire reaction. So, similar kind of strategy we will basically talk about little bit later, but now we will try to summarize till today what we have discussed. At the very beginning we said our strategies will be mainly focused on 6 different topics. Topic 1 is transformation based, topic 2 is functional group based, topic 3 is starting material based. We basically clubbed these 3 strategies together, and in addition we talk about some mechanism based strategies which are also part of this entire 3 strategies. So, strategy A, strategy B, strategy C. Now, we have also formulated remaining 6 strategies which are not very much important, but also plays an integral role. We say strategy like symmetry based strategies for designing a retro pathway. Then we said topology based strategies, and then stereochemical based strategies, So, still today we have basically covered this 3 part, and because this 3 part is the main highlight of elementary courses which I am offering. Now, our remaining part of the lecture will be basically focusing on first we talked about symmetry based strategies, then we will try to talk topology based strategies, and then we will talk about stereochemical based strategies, and then we will have a concluding remark and we will try to sum it up. So, please go through the entire transformation, functional group and starting material based strategies. We will see you in the next lecture. Till then, goodbye.